the difference of two numbers. You say of two numbers? Do you say difference between two numbers? What do you say? The difference of two numbers is 10. Find their minimum possible product. So we have all the tools to solve these problems right now. There's no background information about any of these. First of all, I only see like 6 cameras on. Where's the rest of you? There's Hirsch. Where are all the other people? I need to start waking up. Muhammad, there you are. Okay, so in pre-calculus, you may have done some units modeling with equations. Did you ever do that? Did you ever do modeling with equations? Muhammad, did you do that in pre-calculus? Modeling with equations? Or did you do these Farmer Brown type problems?
Yeah, I think we did.
Okay, so then you did do modeling with equations. Anyone who took pre-calculus here at Rutgers, 111 or 115, you definitely did modeling with equations. So that's the first part of an optimization problem. That's why I bring it up. The first half of all optimization problems is really nothing to do with calculus. Really, literally nothing to do with calculus. It's about modeling the problem. So the first goal is going to be, oops. Where is this? There we go. So the first goal in all these problems is going to be to rephrase the problem as find absolute extremum. Could be min or max depending on the problem. In this case, we want a minimum, right? Find absolute extremum of f on the interval I. That is going to be the initial goal of all of these problems. We will need to reduce it to a 4.1 problem. Okay, so how are we going to do that? So does anyone have an idea of how to start this problem? We need to somehow introduce some language, some variables, some equations, some functions. We need to introduce some of that into this problem in order to reduce the problem to finding the absolute minimum of something on an interval. Now, Jacqueline, you said x minus y equals 10. So x and y, what are x and y, Jacqueline?
Just like any random numbers.
Any random numbers? Well, I would hope that they are the two numbers we're talking about in this problem.
Yeah.
So let x and y be the two numbers. Does it matter which one is which? Not really. Now, Margaret has written a minus b equals 10 and f equals ab. And Jacqueline has written like x minus y equals 10. That's the same thing as a minus b equals 10. Now, these two things have different roles. So I'm going to write them down, and we're going to talk about them separately. So Jacqueline wrote x minus y equals 10, and then Margaret wrote f equals xy. These are entirely different. These two things have entirely different roles in this problem. I mean, they look like two equations, but they're really not. Let's see if anyone can say, what is the role of this thing? F equals xy. Can someone explain the role of that equation in this problem?
It's their minimum possible product.
It is the minimum possible product?
Well, it could be.
It could be. It's the function we're trying to minimize, right? xy represents the product of these two numbers, so f is the function we're trying to minimize. And x minus y equals 10 is something else. So if x and y are the two numbers, let x and y be the two numbers, then the function we want to minimize is f of xy equals xy. Let's be very clear that we're defining some function f here. It really wasn't an equation, it was a function. This has a very special name. Does anyone know the special name of this function for this type of problem? Does anyone read the textbook or watch the pre-lecture videos ahead of time? God forbid you did. Right? So this is called the objective function. And it's going to be very important in all optimization problems to be able to identify this objective function. Again, the objective function is the function you are trying to find the minimum or maximum value of. In this case, we are asked to find the minimum product. So the product of the two numbers, which is x, y, is obviously the objective function. Now, what is the problem with this function? If I wanted to minimize this function right now, what is the issue? There's a very, very obvious, hopefully obvious issue with this function. Two variables, right? So that's how these optimization problems go. You're going to have an objective function with more than one variable. So the goal is to get something else that can reduce this to less than multiple variables, ideally to one variable. Now, x and y are not really independent of each other, right? I mean, this is not a function of two independent variables. X and y are not allowed to vary independently. In fact, we had just discussed it. Both Margaret and Jacqueline had written it, right? Oh no, I put this in orange. Let me put that. The function f has two variables. However, x and y are not independent of each other. Right? Do we understand why that's the case? So, for instance, Caleb, do you understand why x and y are not independent of each other? For instance, if I told you that x equals 15, do you know what y would have to be?
It'd have to be 5, right?
Yeah, 5 or 25, depending on how you label the two numbers.
Mhm.
But yeah, you're right that there's a relationship between these two numbers, so we can't just vary them independently of each other. So we have something called a constraint equation. So we're going to have x minus y equals 10. You can also write y minus x equals 10. All you would be doing is reversing the label of the two numbers. It doesn't really matter, right? So x is obviously the larger of the two numbers, or the greater of the two numbers, I should say. So this is called a constraint equation. So a constraint equation is an equation that is always true, right? That the variables must satisfy. And it's not a function. It's not anything like that. It's just an equation that the variables have to satisfy. That's it. It's kind of like in related rates when you had this equation or relation between the variables. That's it. Okay, so now what do you think we do with this constraint equation? Well, our objective function, I want to find the minimum of, but it has two variables in it. So I need to use my constraint equation to somehow eliminate one of the variables. So the easiest thing to do is to solve for one of the variables in my constraint and then use that to eliminate the variable in the objective function. Okay. So we use the constraint to write the objective in terms of one variable. Now, it doesn't really matter what variable you choose. So let's see. So let's say y equals, I want to solve for y. You want to solve for x? Here, we'll solve for x, whatever. So x equals y plus 10. And so what do we do now? So we substitute this into substitute for x in objective. Okay. So what's our objective? Now, actually, I'm going to go back and change this. I don't want to use the letter f for this. I'm going to use p. So I'm going to use f for the one variable function. So I'm just going to call that p instead of f. So our objective function is now, so instead of p of x and y, right? That was our original objective. Well, x we now know is y plus 10. So I substitute y plus 10 in place of x. And so my objective function is y plus 10 times y, or I can just write y squared plus 10y. So that is my new objective function, and it is written in terms of one variable. And my initial goal is now done. Remember, what was our initial goal of the problem? The initial goal of the problem was to reduce the problem to finding the minimum or maximum of a one variable function on a certain interval. So that part is now done. So I can write what is my goal now. My goal is to find the absolute minimum, right? It was to find the minimum product. So the absolute minimum, find the absolute minimum value of what function. So now this one variable function I'll call f. F of y equals y squared plus 10y. Find the absolute minimum of that on a certain interval. Okay, so we haven't really talked about that yet, right? What is the interval on which we are minimizing this? What is the domain of f in the context of this problem, right? I will say that the interval you're minimizing or maximizing something on is not always the natural domain of the function. Sometimes you have a function you're trying to minimize, and there are other considerations that say, okay, y can only be, say, greater than 3 or something like that. So it's not always going to be the natural domain of the function. So what would you say here? In the context of this problem, so Miriam says all real numbers. So is y allowed to be any real number? Okay, well, let's look back at the problem statement. The difference of two numbers is 10. Find the minimum possible product. Okay, right. There's no other constraint or there's no other consideration that we have to put on this variable y. For instance, the problem could have said the difference of two positive numbers is 10, right? And then the domain of this function would have been 0 to infinity, right? Because the problem told us positive numbers. But there was no consideration like that in this problem. So in fact, the interval is minus infinity to infinity. But we will see later in the later examples that the interval is not always the domain of the function or the natural domain of the function. Really. Okay. So have we done any calculus yet, Justin? No, literally no calculus. So if you took pre-calculus, this was a valid question up until this point, and now we actually want to solve the problem. So that's the modeling part of the problem, and that has no calculus in it at all. So it's expected that first half of the problem, most of you should be very good at that. Okay, so now let's actually do the calculus part. So how do we move on from this problem? Now that we've actually reduced the problem to what's in the gray box, what do we actually do? All right, how do we find that absolute minimum? What would be your first step? Derivative, why are we finding the derivative of the function? Like I said, taking the derivative of the function is always the answer. So you have to tell me why. What is the point of this?
So you would find your critical points.
You can find your critical points, and Justin said we can use the first derivative test. Okay, so let's do that. Okay, so this derivative exists everywhere, right? So there's no consideration of where it doesn't exist. So take a derivative and set it equal to 0. We have 2y plus 10 equals 0. So we get y equals -5. Okay. So here's a question. How do we know that y equals -5? Or rather, so usually when I want to find the absolute minimum value of something, what is usually the procedure? So this you did on the last exam and in 4.1. Do the number line thingy. Is that what we've usually done to find the absolute minimum? I don't think we've usually done the number line thingy. We don't call it a thingy either. We plug it into the original. What did we do in 4.1? If I wanted to ask you, find the absolute minimum of say f of x on some interval, what did you do? You found the critical points, fine. And what else did you do? I don't know what this means, make a critical number chart. I don't know what this means. Let's be specific. So let's say you found the critical points. Okay, you found them. What else do you do? Plug the points and any endpoint into f of x. Okay, so I make a chart with my critical points and my endpoints, and I substitute those x values into my function, and I compare them. Right. What's the issue with this problem? The fact that we have a y doesn't matter. The y is a dummy variable. I could have called this t or z. It doesn't matter what the variable is called. So Justin says no endpoints. Someone says there's only one critical point. Doesn't matter if there's only one critical point. That doesn't really matter. Nothing to compare. Well, I think Justin got it. I think Justin's right when he says there are no endpoints. Now I know some of you were discussing this in the Discord for the last exam. Caleb, isn't there some theorem that tells us when we are guaranteed to have a minimum or maximum? Don't worry, Mohammed, you're next.
It has to be continuous on a closed bound.
It has to be
interval.
continuous. The function has to be continuous, yeah, on a what?
Closed bound interval.
That's right. Remember the extreme value theorem from 4.1. Right? Caleb just reminded us of what it says. If f is continuous on a closed and bounded interval, AB, right? Closed, bounded. Then you are guaranteed a min and max, right? Min and max are guaranteed. However, if you relax any one of those assumptions, so if the function is not continuous, or if the interval is not closed, or if the interval is not bounded, if any one of those three things is relaxed, then the min and max are no longer guaranteed. They might still exist, but they're no longer guaranteed. So in this problem, what do we have? We do have a continuous function, we do have a closed interval, but we do not have a bounded interval. So the min and max are actually not guaranteed to exist, and that is actually a very big deal. To erase that orange thing, I actually have to do this. Okay, so that's a big deal. So I don't even know that the minimum exists. So let's actually figure it out. Okay, so since the interval minus infinity, infinity is unbounded, f is not guaranteed to have both a min and a max. So here's a question then. If you're not guaranteed to have a min or max, is there anything else we can do to somehow argue that this function really does have a min or max? Have we learned anything else in the meantime that can let us determine whether there is a min or max? We can find where f prime of x is increasing and decreasing. Jacqueline says, look for sign change, increasing and decreasing. Okay, so we can use the first derivative to find out if there really is a min or max. Okay, so let's see that. We use the first derivative test or whatever, or I'll just say we use, we construct a sign chart for f prime. All right, so the only cut point was 5, or actually -5, sorry. Sine of f prime. Shape of f, you know the drill, right? Test points. -10 and 0. And then our derivative was 2 times y plus 5. So should be a very easy sign chart, right? F of -10, we can see is negative, and f prime of 0 is positive. So our sign chart for the first derivative goes negative, positive. So we get decreasing and then increasing. So what do you conclude about the nature of y equals -5, the point at y equals -5? It's a local minimum, I should say. We should qualify this. Right now we can conclude it's a local minimum. Now we actually wanted an absolute minimum. Now it is an absolute minimum, so I don't want to give you a different impression. But right now, just from the sign chart, I can conclude it's a local minimum. What else should we observe to conclude that it is actually an absolute minimum, not just local? It's actually also an absolute. What else tells you that not only is it local, it's also the absolute minimum? What do you think? I'll give it a few seconds to see if someone has an idea, and then I'll give you a hint. There are no boundary points? Not quite. Because there's only 2 intervals, you're sort of getting closer. So Caleb's a little bit closer. There are no other critical points. Okay, so I think you got it. So Justin, I think that's correct. So everything else was too specific. So Hirsch, the derivative is linear. That's specific to this function. Michaela, the function is quadratic, only 1 min and 1 max. That's specific to this function. I want something that would be true for any other function that sort of has this. And so what Justin said is correct. There's only one critical point. So think about this. Could there be an absolute minimum somewhere else? Right? So right now I have a local minimum at y equals -5. Right? Could there be an absolute minimum somewhere else? Say at like 6. Could there have been an absolute minimum at 6? Mohammed, why no? You're shaking your head. Why could there not have been an absolute minimum at 6?
Because that's not a critical point.
Not a critical point, right? Exactly. Any other minimum or maximum you would have found had to be a critical point. So let's make that note. So y equals -5 gives a local minimum. Since there is only one critical point, y equals -5 actually gives an absolute minimum. Okay, so now we can actually answer the question. The question said, find what the minimum possible product actually is. So the minimum possible product happens at y equals -5. So the minimum product is f of -5. So that the function was y squared plus 10y. Evaluate that at -5. And so we get -25. Okay. So if two numbers have to have a difference of 10, their product can be no less than -25. Great. So bonus question. What is the maximum possible product? So first, I want to ask the question, to answer this separate question, what is the maximum possible product? What has changed about our work, if anything? This whole entire problem, we were assuming that we were trying to look for a minimum. Now we're looking for a maximum. So what has to be changed? And then as you think about that, then also think about what actually is the answer to this question. What is the maximum possible product? Tricky questions, I guess. A little tricky. Jordan says nothing should change. I think that's right. Yeah, nothing in this problem we ever needed the fact that it was a minimum. I mean, when did the minimum actually come into play? Really never. I mean, everything, we would still get the same exact goal, right? We would still get the same objective, the same constraint. We would still get the same function, same interval. Nothing that didn't depend on the minimum. I would still get one critical point, -5. I would still have the same exact sign chart. So maybe the only thing that'd be different is maybe just right here. You know, at the very last minute when we start to make our conclusion, I'm just interested in answering a different question. But all of my work, literally everything up until this point, has not changed. So now can you answer the question, what actually is the minimum possible product? So given that none of your work has to change, can you now answer what is the maximum possible product? There's no max. Jordan, there is none, it goes to infinity. Justin, would there be none since it goes to infinity? Yeah, there's no maximum. So what you said is correct. This function does have limit infinity at both ends. You can also argue, well, if there is an absolute maximum, that means there has to be a local maximum, and there is no local maximum. So there's a few ways you can argue about that, but there is no maximum. There is none. So there is no absolute maximum, and in fact, as a few of you noted, this function, it's actually in terms of y, this function actually has limit infinity at both ends. So the product can actually be as large as you want. Not only is there no maximum, the product can actually be arbitrarily large. Okay. So just be careful of that, right? Sometimes a question might ask you for a min or max, and it doesn't even exist. And all of that boiled down to the fact that this interval was not bounded, so the min and max were not guaranteed to exist. There was a min, but there was no max. Right? So that shows you that you're not guaranteed. Any questions about any part of this problem? So I kept the problem itself simple so that we can actually see every little part of it, right? The constraint, the objective, the roles of the constraint and objective, how we get it down to one variable, and then this whole last part where we do the sign